Okay, so we resume our discussion on the agreement protocols. In the last class, we had seen that there are various types of models in which fault tolerance in distributed systems is studied. And in the first class that we looked at, we studied the crash faults. So, we tried to see whether we can have a protocol which achieves the agreement or consensus on a value in the presence of faults which can bring down individual processes. Okay. So, they are the crash faults. Crash faults means that they completely, the process which crashes completely goes out of action and it does not participate in any of the activities thereafter. In that context, we saw that in a system of n processes, we can tolerate even up to n minus 1 crash failures and still achieve agreement. We presented an algorithm which works for a given parameter f, it actually runs for f plus 1 rounds, and if the number of faults is less than f, then it guarantees that the algorithm will achieve consensus at the end of f plus 1 rounds. Today what we are going to look at is the Byzantine fault model. So, there is a classical problem which is the origin of the Byzantine fault problem, and that is called the Byzantine and the background of this problem is as follows, that we have a fort and there are several camps for the different battalions. They are positioned outside the camp. They have all together laid siege on the fort, and they all want to agree on whether they are going to attack the fort on the same night or not. And we have two types of generals. So, each of these battalions is led by a general. So, we have some generals are loyal generals. Okay. So, these are the loyal generals, and we can also have some disloyal generals or traitors. Okay. So, there are some traitors. Now, what in the Byzantine generals problem, the traitors are malicious. They want to create a division between the loyal generals. Now, the protocol starts by one of the generals broadcasting its decision whether or not to attack. Okay. So, one general broadcasts the decision whether or not to attack, and then there are the other generals are called the lieutenants, and the lieutenants must then talk with themselves and come to an agreement whether or not to attack. All right. Now, how can the traitors function? What they can do is they can tell some of the loyal generals that he told us to attack, and it can also tell some of the other loyal generals that he told us not to attack, thereby trying to create a diversion between them. Now, the question arises is, what should be the ratio of the loyal and the traitors such that you can still guarantee that the loyal generals agree on the same decision. Is that clear? All right. So, this is the classical Byzantine generals problem. Now, we are going to see several variants of that and also the algorithms for solving the Byzantine generals problem. So, let us look at the model. So, we have total of n processes, at most m of which can be faulty. Okay. Now, we will show that Byzantine agreement is possible for certain ratios between n and m, and we assume that the communication medium is reliable. So, the processes themselves can be good or malicious, etc., but the communication medium is reliable. So, no information gets dropped from the communication medium. We assume that the system is fully connected. So, every process has a direct communication with every other process. So, it is not that the message from A to B goes through C, that is not the case. It is point to point direct communication between processes, and receiver always knows the identity of the sender of a message. So, you cannot impersonate some other general. Okay. So, the sender is known from the message itself, there is no ambiguity about that. The faults can be Byzantine, which means that when a process receives a message, it can send out messages in a malicious way in order to confuse the protocol. Okay, that is meant by Byzantine. We also assume that the system is synchronous, that is, in each round a process receives messages, performs computation and sends messages. Okay. This is the definition of a round, okay, and we will see that all of these processes, all of these protocols have certain number of rounds. Byzantine agreement, also known as the Byzantine Generals problem, is formally defined as follows: that one process X broadcasts a value V, and the agreement condition is that all non-faulty processes must agree on a common value. All the non-faulty processes, namely the loyal generals, they must agree on a common value, and the validity condition is that the agreed upon value must be V if X is non-faulty. Okay. So, if the initiator of the protocol is a loyal general, then all the loyal generals must agree upon the same value as sent by the initiator. Okay. Is that clear, both of these conditions? Now, note that when we talk about a value V, it suffices to assume that V is Boolean, because if it is any other value, then you just repeat the protocol for every bit of that value, right. So, if V is not a single bit, if V is some number, you can represent that in Boolean and then run the agreement protocol for each bit of that value, right. So, therefore, it is sufficient to study this problem assuming that V is Boolean, right. Is that clear? There are two variants of the Byzantine agreement protocol. One is called the consensus, which we had seen before. What consensus means is that each process broadcasts its initial value, unlike in the previous case where it was only the one initiator which broadcasts its value. Here everybody broadcasts their own value, and they must all satisfy the agreement condition, in the sense that at the end of the protocol the loyal generals must all agree on the same value, and if the initial value of all non-faulty processes is V, then the agreed upon value must also be V. So, if all the loyal generals start with the same value, then the agreed value will also be that value, alright. This is one problem, and the other problem is interactive consistency. What this means is that each process K broadcasts its own value Vk. Okay. All non-faulty processes agree on a common vector V1 through Vn. Okay. If the kth process is non-faulty, then the kth value in the vector agreed upon by non-faulty processes must be Vk. Just go through the definitions. Okay. Now, let us look at the last red line at the bottom. We state that the solution to the Byzantine Agreement problem implies the solution to the other two. So, suppose we have a protocol for solving the Byzantine Agreement problem, okay. Then how can we use that to solve interactive consistency? Each we repeat that agreement protocol for each process K, right. So, process P1 starts a Byzantine agreement, at the end of it everybody, all the loyal generals agree on a value for the protocol initiated by P1. Similarly, we have a exact copy of this, except that the initiator is P2, right, and they all collect these values into a vector, and that solves the interactive consistency problem. Is that clear? So, interactive consistency is basically Byzantine agreement individually executed by each of the processes, and the outcomes are collected and put in the form of a vector. Then that vector is a solution to the interactive consistency problem. Is that clear? Any doubts? Anybody?
So, do they have to agree to the value given by the process K, or they can agree to one value which can be different?
Okay. So, the Byzantine agreement problem says that if Pk is the initiator and Pk is loyal, then all the loyal generals should agree on Vk, right. If Pk is the initiator and Pk is not loyal, then all the loyal generals should agree on some value, but that value may not be Vk. Is that clear? So, no, for Byzantine agreement there is no vector, there is only one value V. Okay. So, Pk, suppose it initiates the Byzantine agreement protocol. So, Pk initiates the protocol with Vk, right. So, it is like this, that process Pk starts with a value Vk, right, and at the end of the protocol all the processes, all the loyal processes must agree on the same value. Now, if Pk is loyal, then all of them will agree on Vk, they will all agree on Vk, all the loyal ones will agree on Vk. If Pk is not loyal, then they will agree on a common value, but that value may not be Vk. This is the requirement of the Byzantine agreement protocol, right. Now, what is happening in the interactive consistency is P1 starts a Byzantine agreement, okay, and everyone gets an estimate of V1. So, all the loyal variable, all the loyal ones, they agree on some V1. Similarly, P2 initiates an agreement protocol and every process agrees on some value of V2, all the loyal processes, right, and so on, and Pk also initiates a copy of the protocol and everybody reaches some kind of agreement on Vk, right. Now, what do we have in P1? We get V1 from here, we get V2 from this protocol, and we get Vk from this protocol. So, this is the vector which is accumulated at P1, right. Similarly, some Pi will also accumulate V1 from here, V2 from here and Vk from here. Now, you see that this vector and this vector will be the same, right, which is what is required by the interactive consistency problem, right. That is what is given here, that all non-faulty processes agree on a common vector V1 through Vn. Okay. Is that clear? So, how given a protocol for Byzantine agreement, how we can solve interactive consistency is clear now, is it? Yes or no? Okay. Now, suppose we have solved the interactive consistency problem. Now, can we use that to solve consensus? What is consensus? Each process broadcasts its initial value and they must all agree on a same value at the end, and if the initial value of all non-faulty processes is V, then the agreed upon value must be V. So, given a solution to the interactive consistency problem below, how can we solve the consensus problem? No, but what value will you agree on?
The value which has the highest frequency,
Highest
highest initial number of
value of the process.
You can,
The lowest or the maximum, any one value could be.
you could take any one of them. So, take majority for example. You could take the majority value for example. So, the majority value in all of them, all the since interactive consistency guarantees that this vector will be the same in all non-faulty processes. So, the majority value will also be the same in all the non-faulty processes, right? And if all of the non-faulty processes have the same value V, then that will become the majority value, provided that the number of non-faulty processes are in majority, right? See, after every one of them have agreed on the same vector V1 through Vn, like in interactive consistency. See, look at this interactive consistency. Let me pick up a pen. Yeah, look at this interactive consistency problem. Here, every process, every non-faulty process must agree on the same vector V1 through Vn, right? Now, if all the non-faulty processes have the same vector, then if all of them take the majority among these,
they all have certain different values.
maybe,
They may be same also.
maybe same also. But if they take the majority value, then the majority value will be the same.
Then how do you define majority in this case? How do you define that? Because
If you,
in this case, a lot of processes are agreeing on the same value. But if let's say out of 100 or only 4 5 processes are agreeing on 4.
yeah, so how many are agreeing on 4, how many are agreeing on 5, how many are agreeing on 9, out of those pick up the maximum one, right? That is the majority value. Majority value means the largest number of processes which have the same value.
Then you need to disseminate the value again to everyone.
No, because all of them have the same vector. So, if they apply the same function, they will get the same result, right? And that is the value that all the non-faulty processes agree on. Now, if all of these values of all the values for the non-faulty processes is the same and the non-faulty processes are in majority, then the majority value will also be the same. Okay. So, it will satisfy this condition also, that if the initial value of all non-faulty processes is V, then the agreed upon value must be V. Clear? Actually, we will show that the number of non-faulty processes has to be in 2/3 majority, right? That is the requirement for passing a bill in the house, right? We will see that unless you do that, people can have malicious ways of confusing everybody, right? So, 2/3 majority is what is needed. We will prove that. So, this is clear, right? First thing that we will see is that for the Byzantine agreement problem, because that is the fundamental problem, right? We have shown that both the consistency problem and the interactive consistency problems. They are both solvable provided you have an algorithm for solving the Byzantine agreement problem. Now, we will first show that there is no solution to the Byzantine agreement problem if it is not possible in asynchronous systems. Let us skip that part for the time being. There is no solution possible if the number of generals n is less than 3m plus 1, where m is the number of faulty generals. Okay. So, in other words, we need 2/3 majority to be able to achieve agreement. Okay. And we will also observe that any protocol for solving this problem will need at least m plus 1 rounds of message exchange. Okay. Now, the model in which we will study this problem, the messages that will be sent by the processes between themselves are called oral messages. Okay. So, the messages, the malicious generals can forge or change the messages in any manner, right. Why are we talking about oral messages? Because you are not signing it. Okay. It is just taking one's word for it. So, one general will tell the other general that let us attack, and that general in turn may convey it in the proper way to other generals, or may maliciously tell some people that he told me to attack and tell some other people that he told me not to attack, right. So, we say that these are oral messages because they are not signed, right, and therefore, the malicious generals can forge or change them, but the receiver always knows the sender. So, I will always know that if you send me a message, I will know your identity, and you cannot impersonate somebody else and send the message, right. Okay. Now, let us dive into the proof that we cannot get Byzantine agreement unless the number of loyal generals is in 2/3 majority. So, we will start by looking at a system of 3 processes of which one is faulty. So, that is not 2/3 majority, right, because 1/3 of them is faulty. So, we have exactly 2/3, but not one more. Okay. So, in this scenario where we have a system of 3 generals with 1 faulty, we will show that Byzantine agreement is not possible, okay. And then we will use this result to prove it for the generic case. So, let us look at this. So, in this picture, S is the initiator, okay. U is the faulty general, and T and S are loyal. Okay. Now, S broadcasts its value, let us say 0, to both T and U, okay. And what U does is it acts maliciously. So, it responds to S by 0. So, to S it acts in a loyal way, but to T it acts in a disloyal way. So, it actually conveys that 1 was sent, right. Now, let us see what can T do here. Now, should T decide on 0 or should it decide on 1? Now, see, the initiator will decide 0 because it knows for certain that the decision is 0, because it is the initiator and it is loyal. So, it will decide on 0. Now, T, if it wants to be in the same side as the loyal general, then it has to decide 0, right. Otherwise, there is a disagreement between the 2 loyal generals if this one decides 1, right. So, in this scenario T must decide 0. Now, the symmetric situation where S is the initiator, T is faulty, U is loyal, in this case U must decide 0. by the symmetry. T knows that it is disloyal, U does not know whether T is loyal or disloyal, right. It does not even know whether S is loyal or disloyal, but the point is that if S and U have to agree on the same value, then in this case U has to decide 0. Why? Because S being the initiator, oh sorry, there is a typo here, just let me correct it. Oops. This will be 1, sorry. In this case, because S is deciding 1, you will have to decide 1, because the S and U must agree on the same value, right. Now, in this case therefore, T must decide 0, in this case U must decide 1. Now, look at this third case where S is the faulty general, and what does S do? It interacts with U exactly in the same way as scenario 1. So, you see this interaction, oops, just hold on, let me choose the pen once again. Yeah, this interaction between S and U here is exactly what S does with U here, right. So, with U it performs exactly the type of behavior as in scenario 1, and with T it performs exactly the same behavior as it did in scenario 0. Okay. So, this behavior and this behavior is exactly identical, this behavior and this behavior are exactly identical, right. Now, look at T's situation here. T's situation here is that from T's perspective, see what this scenario and this scenario are indistinguishable, right. It is indistinguishable. So, in this case T will have to decide 0, just like it had to decide 0 here, right. And again, if you look at this scenario and this scenario, then they are identical for U. So, you will have to decide 1 here.
In the first scenario, why is he deciding on 0?
In the first scenario, who is this?
He must decide 0.
That is because S will decide on 0. S is a loyal general. What is the requirement of the agreement protocol? That if the initiator is loyal, then the value of the initiator is the value in which all the loyal generals will have to agree to, right. So, the value of S here is 0, because that is what it broadcasts.
How does T know that is the initiator?
How does
T know that S is the initiator?
that is because S sends the first message. Okay. So, it knows that S is the initiator, but it does not know what is the correct value of S, because it does not know whether S is loyal or disloyal. But the protocol demands, the requirements of the protocol is that if the initiator is loyal, then the initiator's value will be the value which all the loyal generals agree on, right. In this case S is loyal, so T will have to agree on 0, otherwise the agreement fails. Is that clear? Similarly, here S is loyal, so you will have to agree on 1, right. In this case S is disloyal, but it cleverly acts in such a way that for T these two situations are identical, and for U these two situations are identical. That is how S achieves in confusing both T and U. T believes that this is scenario 0, U believes that it is scenario 1. So, T has to decide on 0, U has to decide on 1, and therefore, S has been successful in convincing one general that it is attacked and convincing the other general that it should not be attacked. So, it has succeeded in denying agreement among T and U. Now, is this argument very clear? If you have not followed this argument, then I will repeat that, because otherwise you will not follow what is the.
But when T and U are exchanging their messages, then they don't know that they don't agree with each other.
When
T is sending to U in the diagram.
yes,
T is sending 0 to U and U is sending 1.
right.
They both know, at least they both know that they are not agreeing to
So,
each other.
T knows that okay, what U is sending me is not what I agree to. So, U is agreeing on 0, and it knows that what U sent, when T agrees on 0, okay, it knows that whatever U sent it is not its agreed value, but what it does not know is whether U is faulty or S is faulty. So, what should it choose? If it chooses U to be true, then in this scenario it will fail. If it chooses S to be true, as in this case, then in this scenario it will fail. So, there is no way out, there is always a situation where it will fail, and it has no way of distinguishing between scenario 0 and scenario 2. T has no way of distinguishing it, because the other two are sending it messages in an exactly identical way.
But our the model for the protocol said that if the source is a faulty, then non-faulty processes should agree on a value which is different from what it
May be different,
may, may not,
yes,
may
may
not.
or may not, but they have to agree. It is not happening. So, that is why we are saying it is failing. What we are proving here is, if you have 1/3 of the generals are disloyal, then we are proving that you cannot have agreement. There will always be a scenario where it will fail.
So, if in the third, fourth loyal general, then he would have also given a different value, then they made a.
Then they may have been able to, then they will see a protocol where if we had 4 generals, out of which one is faulty, then agreement is guaranteed. Now, but is this part clear, that why with 3 processes we can, with 3 processes and 1 process being faulty, we can never achieve agreement? Is that clear? You can reproduce the proof if I ask you, right? End semester question? No, is that clear? Very clear? Right. Now, let us think of this, generalizing this proof to a general system of n processes, of which 1/3, at least 1/3 are faulty, right. Now, to prove that, proof is very simple. If you understand this, that proof is very simple. Now, what we do is that we start by assuming the contrary. Suppose there is a protocol. Suppose there is a protocol P, okay, which can work with n generals and n by 3 faulty generals. Yes, n is total and n by 3 is the number of faulty generals. So, suppose there is a protocol which can achieve agreement in this case. Okay. So, let us suppose that there is a protocol P which can achieve agreement with n, this is the total number of processes, out of which n by 3 are faulty. Okay. Suppose there is a protocol. Now, we will show that if there is a protocol like this, then the system of 3 processes is also solvable. But then we have shown that the system of 3 processes in which one is faulty is not solvable. So, that will be the contradiction, and we will establish that no such protocol P can exist. Okay. Is the line of the proof clear? the line of the proof, let me repeat, is as follows. We suppose that there is a protocol which can tolerate up to n by 3 Byzantine failures, right. Now, if there is such a protocol, we will show that there is also a protocol for a system of 3 generals out of which one is faulty. But we have just now shown that there cannot be such a protocol. So, that will establish that there cannot be a protocol P. Okay. Now, how, given such a protocol P, can we construct a protocol for a system of 3 processes? What we will do here is that, okay, out of these n by 3 faulty processes, so let us say, let us club them. So, these are the n by 3 faulty processes, okay, and the remaining 2/3 of them, let me split them up into 2 parts, each having n by 3. Okay. So, these are the traitors. So, we have put all the traitors, right. Okay. Now, you are saying that for such a system P will give us agreement. Okay. Now, what we do is we say that, okay, in our system of 3 processes, let us call the 3 processes PA, PB and PC. In our system of 3 processes, let PA simulate these n by 3 generals, let PB simulate these, and let PC simulate these. So, actually we have only 3 processes, but whatever these n by 3 processes would have done in the system of n processes is what PA itself does. Okay. So, it is mimicking the behavior of these n by 3 processes, it is doing everything locally. PA is supposing that all the n by 3 processes are in its local site, and it is simulating that, right. PC is doing, sorry, this is PB. PB is doing the same for these n by 3, and PC is doing the same for the traitors, right. Now, if this protocol is correct, then at the end of this protocol, these processes and these processes will all agree on the same value, but then that is the value, then that is an agreement between PA and PB, right. So, that shows that if there is such a protocol, then this system of 3 processes PA, PB, PC will also reach agreement by simulating that protocol by looking at n by 3 processes in each site. Okay. But then we know that PA, PB, PC cannot reach an agreement when one of them is faulty. So, we reach a contradiction. Yes.
We are using the factor 3 here.
Okay. That is a good question. What Anvesh is asking here is that in this proof, where did we actually use this factor 3, right. So, what you are saying here is, what we were saying here is that in each of these, okay, each of these is mimicking. So, why could we not have done the following thing, for example, that I have n by, I have just 1 here and I have 2n by 3 minus 1 here, what difference would that have made?
In the previous case, PA should have sent n by 3 messages to PB. In this case, it will send only one, so there will be a weightage that will be given, and that way we can.
No, just look at our argument. What was our argument? Our argument was that if we have a protocol which can solve this problem for n processes, out of which n by 3 are traitors, okay, then we also have a protocol for a system of 3 processes in which one process is a traitor. Okay, right. Now, one thing is that we put all the n by 3 traitors in one bag. Now, that is justifiable, because I want that all the malicious behavior to be contained in one process. But the splitting of the remaining processes into PA and PB, the question is, why does it have to be equal? No, but why do we need equivalence? It has to be recursively proved. Okay. So, I am just giving you the overview of the thing, I mean the logic, right. Now, to prove this recursively, we have to show that how the reduction from the set of 3 processes into this problem. So, what are we trying to reduce? We are trying to reduce the agreement of a system of 3 processes into the problem of agreement among n processes, out of which n by 3 are faulty. If we are able to do that reduction, then we can argue that if you have a solution for this, then we have a solution for this, right. But then we have shown that we do not have a solution for this. So, we argue that you cannot have a solution for that. Okay. Is that argument clear?
But sir, that way we are proving for all n's that are power of 3. If you are
Not power of 3, multiples.
Not multiples, then because we are doing recursively, and suppose it is 6, then we will have it for 2, and we are not trying to prove it that way. Every group has to have multiple of 3 at every stage, so it should be power of 3. We are doing it.
No. First of all, it does not have to be exactly divisible by 3. Okay. What we want is that the number of faulty processes should be strictly less than n by 3. Okay. So, if floor of n by 3 is less than n by 3, then that is fine. Understood? It does not have to be exactly divisible also. It is very simple. We need that at least 2/3, more than 2/3 of the processes will have to be loyal, because we have seen that for exactly 1/3 there is no solution, right. Alright. What I would suggest is that you spend some time thinking about this thing, and then we will discuss it once again. Okay. In the next lecture, we are going to look at the algorithms for solving Byzantine agreement.